Hello everyone, my name is Iakovos Kolokasis and today I'm going to present our paper Say Goodbye to Off-heap caches, On-heap caches using memory mapped.io. This is a joint work with Anastasios Papagiannis, Fivos Zakak, Polybos Pratikakis and Angelos Bilas. In this presentation, I will discuss about big data systems that need to process data in memory, but the data grow faster than memory. Big data systems cache large amount of intermediate results in memory to speed up machine learning workloads. Today, big data systems demand more memory because analytics datasets grow at a high rate. As shown in the graph, from an analysis made by Syncgate, the global data expected to grow 3 times until 2025. As a result of that, big data systems require terabytes of memory per server to keep up the processing. Let's see how caching impacts the performance of 3 well-known machine learning workloads in Spark: linear regression, logistic regression, and SVM. With the blue bar, we show the performance of each workload when no caching is applied, but they recompute the intermediate results on every iteration. With the orange bar, we show the performance of each workload when caching is applied. Jobs in the different workload cache intermediate data in memory to be reused by the next operation. Caching reduces execution time by orders of magnitude compared to recomputation. For example, in our experiments, SVM performance improves up to 90% compared to recomputation. Naively, caching all data in memory means that you need large heaps, and having large heaps means that you need large capacity of DRAM. But DRAM capacity scaling reaches its limit. Today, DRAM scales to GB per DIMM, and the total DRAM capacity in a server is limited by the number of available DIMM slots. On the other hand, fast storage devices scale to terabytes per PCI slot at a lower cost compared to DRAM. As a result of that, today Spark uses the large capacity of fast storage devices to locate large amount of cache intermediate results off-heap. Here we show Spark executor memory. Spark executor memory is divided into 2 logical spaces: execution memory and storage memory. Storage memory is used as an on-heap cache that locates all the cache intermediate results. In Spark, the cache intermediate results are stored in immutable data structures named RDDs. Let's say that we have a very large heap with a very large on-heap cache, and we can locate all the cached RDDs there. Then we have to pay high garbage collection cost because the garbage collector needs to traverse all these cached RDDs on every garbage collection cycle. If we try to reduce the garbage collection cost using a smaller heap with a smaller on-heap cache and a large off-heap cache over a fast storage device, then Spark locates at first the cached RDDs on heap, and if a new RDD is going to be cached, Spark is going to cache it on heap and then serialize and evict some older blocks on the fast storage device. These introduce high serialization deserialization cost because this operation happens on every iteration. In summary, here we have a trade-off. If we have a very large on-heap cache, we have to pay high garbage collection cost. But if we have an off-heap cache, then we have to pay high serialization deserialization cost. In our approach, we try to merge the benefits from both worlds using a very large heap with no serialization and a low garbage collection cost. To achieve this, we propose TeraCache and design for multiple heaps with different properties. We are going to explain how we reduce the garbage collection cost and how we grow TeraCache over a device. We observe that big data analytics computations generate mainly 2 types of objects: short-lived objects that are managed by the runtime, and long-lived, similar lifetime objects that are managed by the application. Based on this observation, we propose 2 heaps. The first heap is fully located on DRAM and is garbage collected, and this heap locates short-lived data objects and is used for computational usage. The second heap is never garbage collected and contains a group of similar lifetime objects. This heap is memory mapped over a fast storage device to eliminate serialization. For this reason, we split Spark executor memory in two heaps. We set execution memory on a garbage collected heap and storage memory in TeraCache, a non-garbage collected heap. We organize TeraCache in region, and every region contains similar lifetime objects as a result to reclaim entire region instead of individual objects in each region. Currently, in vanilla Spark, the JVM is unaware of caching operation as a result to treat cache data objects as short-lived objects paying significant garbage collection time. In our approach, we modified Spark to notify JVM via annotation on every caching operation. As a result of that, the JVM finds out the cache RDD and all its references and moves them to a region in TeraCache. However, we have to do the separation of heaps carefully in order to avoid pointer corruption between objects in the two heaps. Here we show the JVM heap, which is garbage collected, and the TeraCache heap, which is non-garbage collected. There are objects in both heaps. Let's say that we have an object in the JVM heap that an object from TeraCache points to this object. When this object is going to be marked by the garbage collector and be reclaimed, then we will have an entangling pointer and our system will crash. In order to eliminate backward pointers from TeraCache to JVM heap, we move the transitive closure of an object to the TeraCache region. Also, we allow forward pointers from objects that reside in JVM heap to objects that reside in TeraCache heap. But we stop the garbage collector to traverse TeraCache heap. Finally, we allow internal pointers between objects that reside in TeraCache heap. As we said, we split executor memory into two heaps. We set execution memory on a garbage collected heap that is fully located on DRAM, tier 1 part. Also, we set storage memory on a TeraCache heap that is memory mapped over a fast storage device. The rest part of the DRAM locates the memory mappings of the TeraCache. But we need to find the best point between DR1 and the DR2 as a result to take the fully advantage of DRAM. This could not be easily and cannot be statically because we have iterative jobs that reuse cache data. As a result to need large space for DR2 to locate more memory mappings and have fast access time in TeraCache. On the other hand, we have shuffle jobs that produce short-lived data. As a result, we need large space for DR1 in order to minimize the garbage collection cost. In order to deal with the DRAM resources for multiple heaps, we ran a set of experiments using k-means and linear regression with different size of DR1 over a total DRAM that is 32 GB. When DR1 size increases, the DR2 size decreases. K-means jobs produce more short-lived data. As a result, when we increase the DR1 size from 4 GB to 8 GB, the total execution time decreases up to 3 times. This happened because in 4 GB we have more minor garbage collections. On the other hand, linear regression jobs reuse large size of cache data. As a result, when we increase the DR1 size from 8 GB to 16 GB, the total execution time increases up to 2 times. This happened because in 16 GB we have more number of page faults. So, the DRAM division between DR1 and DR2 cannot be statically, but have to be dynamically. So we propose a dynamic resizing policy of DR1 and DR2 based on two measures: the number of page fault rate in memory mapped I/O and the number of minor garbage collections that happen in DR1. Now let's see our preliminary evaluation using an early prototype of TeraCache based on parallel GC. In our prototype, we place new generation on DRAM and old generation on the fast storage device. We explicitly disable garbage collection on old generation. Our prototype implementation tried to evaluate the garbage collection overhead and serialization-deserialization overhead. We do not support reclamation of cache RDDs and dynamic resizing. Here we show the preliminary evaluation results of 4 well-known machine learning workloads in Spark: K-means, linear regression, logistic regression, and SVM. The blue bar of each cluster shows the performance of each workload when we use a heap that is swapped over a fast storage device using Linux kernel swap mechanism. The white bar of each cluster shows the performance when Spark used hybrid storage level. Hybrid storage level, Spark cached some RDDs on-heap and the rest are cached off-heap over a fast storage device, paying significant serialization-deserialization cost. The third column with the gray color shows the performance of TeraCache. TeraCache improves performance up to 37% in linear regression and on average 25% compared to hybrid. Also, TeraCache improves performance up to 2 times compared to Linux swap. Swap is much slower because JVM cannot handle where each object is located. Furthermore, we show the performance in garbage collection. We show the garbage collection time for hybrid and TeraCache. TeraCache improves garbage collection up to 50% in logistic regression and on average 46%. The garbage collection improves in TeraCache because we avoid to traverse cache data objects on every garbage collection cycle. To conclude, we propose TeraCache and JVM Spark code design that is able to support very large heaps. TeraCache reduces garbage collection time using 2 heaps and eliminates serialization-deserialization cost. Also, we propose dynamic sharing of DRAM resources across heap. Furthermore, in our preliminary evaluation, we show that TeraCache improves Spark machine learning workloads performance by 25% on average. Finally, TeraCache could be applicable to other analytics runtimes. Thank you for your attention. If you have any question, please reach me via email.